Many living things have the sense called magnetoreception, which means that they can detect magnetic fields. It's been proven that they possess this ability to orient themselves by Earth's magnetic field. But there's still controversy about exactly what the mechanism is, and people simply don't know. Now, humans don't have magnetoreception, but we have other ways of showing magnetic fields. And one main way is with compasses. A compass itself is a lightweight magnet. Anything that could be magnetized and is free to move could act as a compass. The north pole of a compass always points towards the south pole of a magnet because opposites attract. Then why do our compasses point north? Because underneath the north pole is really the south pole of a magnet. You can test this by putting the same compass that points north near a magnet, and you will see the red north point of the compass points away from the north end of the magnet and towards the south end. Records of ferromagnetic rocks show that the Earth's magnetic field flips from time to time. No one knows why that happens or when it's likely to happen again. The Earth's magnetic field is also important because it protects us from radiation, and incidentally it causes the northern and southern lights. This happens because the Earth's magnetic field extends way beyond the atmosphere. The magnetosphere extends tens of thousands of kilometers into space, which is just as well because out there it is deflecting the solar wind, which is made up of charged particles, mostly protons, streaming out from the sun. If not for our magnetosphere, the solar wind would have stripped away our upper atmosphere, including the ozone layer, and we would be exposed to a lot of UV radiation. It always takes a moving charge to create a magnetic field. Anytime a current flows or a charge moves, the region around it will contain magnetic field lines. But what about permanent magnets? The reason they have a magnetic field is that the orbital motion and the spin of electrons creates tiny atomic current loops, which produce magnetic fields. So each electron acts as a tiny magnet. In atoms, electrons can be paired or unpaired. If they're paired, then they will line up as you see at the bottom right, with a spin up, which would have a north pole upwards, and a spin down with the north pole downwards, able to be quite near each other. So they line up just like a pair of bar magnets. If you try to stack them together, they want to line up with north and south next to each other. So different elements, of course, have different numbers of paired and unpaired electrons, and that produces different types of magnetic properties in materials. At the beginning of this lesson, we recalled Gauss's law for electric fields. Well, there's also Gauss's law for magnetism, and that is that the amount of magnetic flux going into a volume of space must equal the amount of magnetic flux out of that volume. So there can be no net flux through the surface of any volume. This is different from electric flux, where you can have net flux out of a volume if there is a charge inside it. That means that magnetic field lines never start or end. They must go in complete loops. Unlike electric field lines that can begin on a positive charge or can end at a negative charge. So that means you can never get a north pole on its own, like you could get a positive charge on its own. It has to have a south pole with it. So why is that the case? Why do magnets work like that? Remembering that permanent magnets are essentially populations of unpaired electrons, and that each electron creates a bit of magnetic field because of its movement, how would we cut that electron in half to get one pole on its own?